Hey
Okay.
everybody, I'm Jared Longfox, one of the hosts of the AIAA Space Resources webinar series, along with Joe Kenrick here. I'm from Lunar Outpost, I'm from the University of Central Florida. Joe is from Lunar Outpost. And today we have Dr. Frankie Zhu of the University of Hawaii here to present on her work in intelligent robotic systems as it relates to space exploration. So, without further ado, Frankie, take it away. I'll be here if you guys need anything. And folks, feel free to punch questions in the Q&A. We'll get to them at the end. Thanks, and take it away, Frankie.
Great. I just want to make sure that you're seeing my screen.
All good, looks great.
Okay. Thank you so much, Jared and Joe, for having me. So, again, I'm Frankie. I'm an assistant professor at the University of Hawaii, but I will be moving to Colorado School of Mines come January of next year. A little bit about myself. I did all of my degrees at Cornell University, the most recent of which was in aerospace engineering. But now I am situated in the Hawaii Institute of Geophysics and Planetology. Because my research is so interdisciplinary, I have a lot of affiliate faculty status relationships with mechanical engineering, electrical engineering, information computer science, earth and planetary science, and more recently, ocean resource engineering. But I won't talk about underwater robots. But yeah, so with this talk, I'm going to get started on my research about autonomous robots traversing extreme terrains. Okay. I will set the context for this talk with a picture of Curiosity temporarily stuck in sand, and then this is Curiosity's journey since landing. As a review, since landing at Bradbury Landing, Curiosity has traversed a diversity of terrain: sand, ice, uneven surfaces, slopes of varying degree to get to this vista point right here, which is called Vera Rubin Ridge. So I'm interested in autonomous robotic exploration on extreme terrains, particularly for aerospace applications which stress limited resources and safety critical operations. The Mars rovers are prime historical examples of this type of research, but analogous problems are also in future rover missions on the moon, with the Artemis program ramping up, and here on Earth, such as search and rescue missions for military or natural disaster relief. Now, exploring extreme terrain is important because for planetary exploration, we want to understand as much of the surface as possible. And coincidentally, the most scientifically interesting destinations are also those that are most difficult to reach. But exploring extreme terrain is also difficult. It's hard to traverse this varied terrain, governed primarily by granular mechanics, especially if you've never seen or mapped the terrain, and as illustrated with the Curiosity rover temporarily stuck in sand. Okay, so I'm going to get this video playing. There are a number of reasons why autonomous and safe exploration on extreme environments is hard. On the right is a popular compilation of fails at the DARPA Robotics Challenge in 2015. I know that robotics has gotten better since then, but I think that this video properly illustrates all of the reasons why autonomous robotics is hard. So, Sum in 2002, I think, listed the problems that robots face in a very succinct way. Robots must operate with only partial knowledge, depending on their installed sensors and then their perception algorithms. Robots must also safely move at speeds related to their dynamics. And so you can see in the video, there are these bipedal robots, and they have a particularly hard time reacting in time to their own leg dynamic modes. Whereas the danger for rovers, which I study, are wheel slippage or other friction events. That touches on terramechanics. Um, Terramechanics includes like the granularity of soft soil or the unevenness of the terrain due to rubble or debris. Robots must also make decisions quickly or for near continuous motion. Okay, there is a lot of processing happening in real time on board the rover or the robot, and when computational processes are simplified at the sacrifice of accuracy, you can have some catastrophic failures like we're seeing. And then finally, robots must be aware of both local motion constraints and global path planning goals. Getting from point A to point B must be broken down into smaller steps that can be acted upon immediately, but with cognizance of the restrictions of motion or the hazards and obstacles along the way. And this is a problem of scales. The rest of the presentation is going to be a response to these problems posed by IRMSUM with my solutions in the context of near future space exploration. All right. So, to solve the problem of autonomous and safe exploration of extreme terrains, there are a series of algorithmic steps we must define for the robot. For me, I like to start with the definition of the science goal and codifying it into an objective function. Here you'll see Viper on the bottom left. I know, RIP, but there is still hope for Viper to be an actual mission on the moon. But it was originally planned to prospect for natural lunar resources, especially water ice, and to characterize geotechnical properties within a PSR, or permanently shadowed region, near the lunar South Pole. If you can see in this depiction of Viper, there was this drill on board that would measure the resistance of the lunar terrain while drilling. And then this picture on the right is a figure generated by my collaborator, Dr. Shuai Li, where we have the lunar surface in the North Pole and the South Pole. And what you're seeing in color here are densities of hydroxyl, where dark purple is more hydroxyl, so the higher presence of water ice. These are the two science goals that I'm motivated by to prospect for water ice and to map geotechnical properties of lunar terrains. And so my lab has built and tested our own versions of these payloads for in situ investigations. On the left, what you're seeing is a spectrometer which measures light reflectance so robots can find ice. And I'm very sorry that I'm an engineer and not a planetary scientist, so I know that the science portion is like not the most rigorous, but is our version to incorporate it into autonomous robots. The point is not so much the science as it is just good enough science so that it can inform autonomous algorithms. This video on the left is Crystal explaining how we choose locations to sample, how to calibrate the spectrometer, how to measure our target, and what good data looks like. And then on the right, we are also motivated to measure the strength of the soil, and we chose to build a bivometer, which measures the load associated with penetrating a certain height of soil. Intuitively, you have to push harder on a plate that digs deeper into the soil, kind of like a drill. And here, Paulo is talking about how to select a good site to sample and how to collect data. Our lab tested these instruments at a lunar surface analog site in 2023 and also earlier this year, and we sampled at 3 different sites. Here is this gorgeous time lapse that we took within a crater bed, sampling at different locations within a field site. So maybe you can make out the people, but Hao is in blue, Crystal's in purple, and Nina's in the yellow vest and orange hat. Paulo's in the orange vest, and Christian's in that yellow vest. We visited these sites because the regolith material is very similar to the lunar surface. Both surfaces are heavily basaltic in nature. The distribution of sand to rock clusters heavily mimic what we see in lunar environments, and we chose sites that didn't have much organic matter because that is representative of the moon. The planetary surface analogs that we tested on are on the Big Island. Specifically, the place we went to was in the Mauna Kea State Park, and just out of frame is the Ellison Onizuka Visitor Center. These planetary surface analogs are helpful to us as scientists and technologists to emulate mission operations and conduct experiments that are close to the real deal spaceflight mission. And just to make a point, this is a very bad Photoshop of our field site and the moon, but what you're seeing now is a blend of an earthly scene in the foreground and our lunar background to make a point that there are some places on Earth that look like the moon and Mars. And to drive the point home, here's the full picture of the lunar surface taken during the Apollo missions. The intention behind my lab is to develop and test algorithms that are as flight traceable to space missions as possible, which is fitting as the Artemis program seeks to prospect the lunar surface for ice and characterize the terrain for future habitat construction. All right, so back to autonomous exploration. The next step in our robot's journey is to make decisions with information from our payloads. For this project, remember one of them was measurements from a spectrometer. I am proposing this decision algorithm called active learning, which is an iterative algorithm that uses historical information to inform where to sample next. So I'm going to explain this animation on the right here. This essentially shows how active learning works. So in the top left, let's say that we drop the Viper rover randomly onto a lunar surface with no a priori knowledge. So here in the top left, this colored surface is a topography of the lunar surface, so a real digital elevation map, and that black star is the rover, and then its black tail is its trajectory. So at every single iteration, Viper collects some measurement by drilling into the icy regolith, and then the spectrometer reads the amount of water that is mixed into the regolith. On the right, what we see is that the rover then learns a model predicting the distribution of water ice, and it also characterizes its uncertainty of those predictions. So what we're seeing here is a colored surface, which is the ground truth of how much hydroxyl is distributed across the surface. And then that gray surface is the rover's learned model, learned prediction of the amount of water ice across the surface. And you're seeing that over the iterations, as the rover collects more samples, that gray surface collapses to the colored surface. And that's great. That means the rover is learning an accurate representation of the ground truth. The way that active learning works is we characterize uncertainty, and that is visually depicted with those vertical gray bars. At every iteration, this rover updates its model, but then characterizes its uncertainty in some kind of prediction horizon around it. And it will choose the spot to sample next that has the highest uncertainty, which is represented with the highest vertical bar on that plot. And so we do see the performance of this algorithm on the bottom subplots where the variance or uncertainty of the model as a function of samples or time goes down as the algorithm selects more and more samples. And this is intuitive because at the beginning, the rover can be continuously surprised by the measurements that it's carrying on. But then as the rover learns more and more about its environment, the measurements, the uncertainty goes down over time. So that is a direct result of the algorithm, but an indirect result of the algorithm is that the accuracy improves. We measure accuracy in root mean square, which is on the bottom right here. And so we want to see root mean square approach 0. And we do see that by optimizing for uncertainty in the information, we can indirectly get a very accurate depiction of how much water ice is distributed across the surface. Okay, so in summary, I am a huge advocate for active learning, which is a type of autonomy. I think that we've proved in numerous papers that these intelligent autonomous algorithms converge on more accurate models of the environment with less samples than, say, a naive snake or spiral exploration pattern. And this kind of performance gain is super important for finite resource missions in space. We're seeing more and more autonomy adoption in space, which is really exciting. And I think active learning is an answer to how we scale the number of missions we operate with a smaller number of human operators on Earth. Okay. The next aspect of autonomous exploration is arguably situational awareness and hazard planning. So instead of suggesting interesting places to go, which is what active learning was about, hazard detection suggests paths to avoid, or it reduces your options. We have the capabilities in my lab to simulate the rover, its environment, and sensor measurements to emulate what a sensor actually sees. And this is what the video right here generated by Ashton is doing. We are operating in a Ross gazebo environment. where there are stereo cameras on board the rover, and through some computer vision techniques, the rover builds a map of hazardous features in the areas, which we depict with these blue-purple pixel grids right here. And the rover then avoids these features during its traverses. All right. The next step to a dynamics model the next step to autonomous exploration is to learn a dynamics model between the vehicle and the terrain. And this interaction is called terramechanics. Here is a free body diagram of the forces that are acting on a rover. Let's say it's a four-wheeled rover, and all of the external forces are coming from the contact interactions between the terrain and the wheels. So what we really want to do, what my lab really wants to do, is to predict the state of the vehicle interacting with the terrain. And fundamentally, it's a regression problem. We are trying to build a map between the current state of the rover, the model parameters, and some control inputs, find that mapping to the next state. So state in this case would be the rover's position, orientation, and its velocities. And so what we can do, we can choose a structure of the model F, and we can choose then implicitly what the model parameters are that reside in F. The things that are constrained are the current state and the control input, but what we can do is formulate this regression problem as an optimization of, we want to find the arguments of model parameters that minimize the error between your model prediction and then the actual measured state. And so I'm going to talk about a lot of different models that we could use in this problem, and then the implications in the dynamic state prediction. Okay, so how do we create a good dynamics model? To learn a good dynamics model that describes your real system, we need mobility and sensor data. We then need to process it through a system identification method to generate a terramechanics model, which has some model parameters, some mathematical structure, and yields a vehicle state prediction. Some data could include imagery of your environment, which then yields visual odometry. It could include your orientation, like roll, pitch, yaw. It could include angular velocity and acceleration. And then you could also extract your wheel motor torque and steering angles. An analogy can be made about how we can use our eyes to visually estimate our position and velocity, how our ears can estimate our orientation and spin rate, and how we can feel in our muscles and joints how our limbs are situated, which are like the wheel measurements. And if I could continue this analogy a little bit further, the way that humans estimate how we move, an example is something called motor babble. It's a common phenomenon in babies where a baby will randomly move their arms and legs, and with enough visual and haptic feedback, we can figure out their dynamic, they can figure out their dynamics and become more coordinated. So we are trying to formalize this learning process in rovers with a method called system identification, where we ultimately generate this dynamics model, but in a more formal way for robots because they talk in, numbers. Okay. There are many different types of dynamics models. So here I'm showing a trade space of dynamics models as measured in prediction error, which is the y-axis. And then on the x-axis is computational intensity. And so the solution space of what kind of models we could choose kind of reside on this Pareto front. And I'm going to be talking through all of these different solutions. But what we really want is a model that is low in prediction error, so accurate, but also low in computational intensity. We want it to be lean and predict very quickly. As of right now, my assessment of the dynamic model trade space is that we don't have a model that is in this desirable zone. And so a lot of my lab effort is to try and push these models towards that desirable zone. All right, so The least computationally complex model is a set of kinematic equations depicted here, which is just integrating velocity and acceleration over time to update your position and velocity. Just super basic, not very accurate. If you were to increase in accuracy, you can derive physics-based differential equations. Here, what you're seeing is an expansion of the kinematic equations by adding forces into the equations. So here, Bailey, who is a PhD student working with me, has scraped the geotechnical and terramechanics literature to see what kind of forces are acting on a wheel. And so here are the three components of force that he has put together from all the literature, and they are informed by these geotechnical properties of the environment. So you can describe force acting on a rover if you know aspects of the terrain, such as cohesion, soil density, Becker coefficient. And so this is one way of representing the physics that is governing rover terramechanics. But it's, more computationally intensive, albeit more accurate as well. The next candidate solution for dynamics models is to use a broad array of machine learning models. My lab has investigated physics-informed neural networks and sparse identification of nonlinear dynamics, where we're using essentially machine learning models are trying to use as data agnostic models as possible, trying to form these universal bases functions, so like essentially mathematical building blocks, to be universal approximators of the data. We have specifically tried to use machine learning models that incorporate physics. So in this case, there's this machine learning method, a neural network on the left, but then it is constrained by partial differential equations on the right. That is one way of incorporating physics into machine learning. And then we've also used sparse identification of nonlinear dynamics, which is essentially this mathematical expression library. And we implicitly fold in the assumption that physics models are very sparse mathematical expressions. And so there's this method called regularization where you try and fit coefficients to a bunch of mathematical expressions, but then you weed out the less dominant mathematical expressions in this regularization step. Anyway, the whole point of this is that PINs, physics-informed neural networks, and SINDI, sparse identification of nonlinear dynamics, are candidate solutions for representing terramechanics. But there is still some improvement towards their prediction error and computational intensity. Another model that we could use are called soil contact models. These are getting more computationally intense. The way that soil contact models work is they calculate the deformation of a surface network of nodes, which is depicted right here. Some geometry, let's say a rover wheel, penetrates each node on the surface, which represents the terrain, and then the node calculates how much force pushes back on the wheel. The force across this area of penetration is kind of like a pressure map, and integrated across all nodes can be thought of a single force on a wheel. This is the method that we chose to implement in our terramechanics simulation, as this method is very accurate but needs more compute power that is only accessible on ground computers. So currently this simulation does run in near real time, but it uses a huge amount of RAM. Computers on board rovers may not be powerful enough to run these soil contact models, so there's still effort to making this push closer to the desirable zone. We do have some really cool videos of it. Here is the soil contact model that Brett, an undergraduate student that I was working with, put together in Ross and Gazebo. What I just want to illustrate here is you can see the compression, the compaction of the soil beneath the wheel treads. And we did some field testing on a beach in Oahu, and you can see that kind of phenomenon emulated in some real world data. which is really neat. This gets us one step closer to an accurate representation of the rover's position over time. And then finally, the last model that I will talk about is the most computationally intense, but arguably the most accurate model that we have so far. This is using discrete element methods. And so these pictures showing right here is showing the interaction between these discrete particles, where every single grain of the soil of the sand is modeled as an independent particle that interacts with all the other particles. The difference between this model and the soil contact model is that the soil contact model was this surface network that did not allow particles to act independently. Nodes only interacted with immediate neighbors, whereas these discrete elements can lift off the terrain surface, and then physics must be emulated for each of these particles. To simulate a terrain surface, you would need to simulate billions of particles that would only cover the ground immediately beneath you, and just a little bit around. On top of this limited spatial range of the method, this method would take a week to crunch through a dynamic simulation for this vehicle traveling over a couple of meters. This method is computationally prohibitive to upload into a rover's head and also cumbersome for algorithm development because these simulations take so long to run and to iterate on. All right, the last piece of this process of autonomous exploration is learning how to control a vehicle to follow some reference trajectory to get where you want to go. And that first equation right here, the control policy is called G, and essentially we are trying to find a control policy that takes into consideration the state of the rover, the parameters that populate your policy G, the current control input, and then some desired next state. We are trying to figure out the next control input that will minimize the difference between your state and the reference state. Okay, but intuitively, just visually, let's look at the video on the left. So this is a very simplified illustration of a rover, which is that red dot, on a slanted surface. It's inclined to 30 degrees, which is the maximum angle of repose for, say, soft sand. And this slope is very slippery. It has a very low coefficient of friction relative to, say, like rock or concrete. What the rover is trying to do in this case is follow this reference trajectory, which is a blue dotted line. And the way that it can do that is learn a dynamic representation. So it's learning the coefficients of friction, and then it is toggling what my steering angle and wheel speed should be to follow this reference trajectory. What you're seeing here is the rover governed by some very basic control policy at the beginning. It's called a pure pursuit controller, where it's just trying to point at the reference trajectory at some look ahead distance. And so we're using this very basic control policy at the beginning to gather information about how the robot is interacting with the environment. And then once the rover learns the environment well enough, then it snaps to this learn controller where it follows that reference trajectory perfectly. Okay, now all together, the pieces of an autonomous exploration algorithm include defining a science goal, codifying it into an objective, incorporating science measurements into some decision-making process, which leads to path planning, also being aware of your environment, which is a path planning consideration. The robot then learns a dynamics model between the vehicle and the terrain, which is a type of terramechanics model. And then finally, the rover learns how to control itself in a terrain to follow some reference trajectory, which leads to a policy generation. To put all of those pieces together, I kind of want to put you in the perspective of a rover just landing on the moon. So let's go through this flow diagram together that emulates the sequential process of how a rover would think about exploration. So imagine that you are the rover and you just landed on the moon. before you even open your eyes, you wake up and you feel this internal motivation encoded into your being that says, map out the distribution of ice within this environment. And after meeting some criteria of knowledge, go to the place that you think has the most ice. With this internal drive, you open your eyes and you take in some information. You note your location and then you measure the amount of ice beneath you. What you're then going to do is update your internal model of how much ice you think is around you. And then you decide whether you want to explore or whether you have enough information to just go to the location of most water ice. At the beginning of this journey, you will err on the side of exploration so that you can gather enough information, and then you'll transition to, exploiting your objective function. It's not always a one-way process, though. During the exploitation phase, you could get a measurement that's totally surprising and then decide you have to explore more to resolve the new uncertainty in your model. So you take your first step and you evaluate how close you got to where you wanted to go. And then given how close you got, you update your understanding of how your control inputs move your body. You move again, and then this is the beginning of the cycle that will just keep on going and going until you, the rover, achieve your goal. So again, you, the robot, you take a measurement, you measure your state, you update your internal model of how much ice is around you. You now have 2 sample points, and you can start to draw a distribution, at least in the direction of more or less ice. With that same measurement, you can evaluate how well your dynamics model predicted your current state, propagating from the previous state. You update your dynamics model with the best guess of environmental parameters. And then simultaneously, you decide to explore or exploit, which gives you the next waypoint you want to go to. And finally, you evaluate how well your rover tracked that last waypoint and update your control input to get to that next waypoint. Thus continues the cycle on and on until you are on the largest ice reservoir in the proximity of where you started. I'll end the planetary robotics research talk on these 2 videos of remote controlled robots that we program to track some kind of reference trajectory or to map this planetary surface analog. And so what you're seeing here, I know it's a little underwhelming, but what you're seeing here is an RC car that is autonomously tracking this circle. A difficulty in robotics is to connect the algorithm to the real rover, which has computational limitations that affect the speed of which your brain can think, which then affect the stability or reaction time that your rover can act. So this will be more pertinent in steep slope environments where the dynamics has smaller time constants. And the reason why I'm showing this seemingly underwhelming video is because having your algorithms work in real life, in real time, is immensely tedious, but incredibly important. I'm of the philosophy that we need hardware demonstrations to be convinced that the underlying algorithms are useful. And so here is a dynamics, model learning, and control policy generation demonstration. Over here on the right is a demonstration of an active learning algorithm in real time in a planetary surface analog. Okay, and so that was the end of the research talk. I'm going to give a quick shout out to PISCES, who enabled me to be able to do the field testing at Mauna Kea State Park. So PISCES is the Pacific International Space Center for Exploration Systems. They are an aerospace research and education program at the University of Hawaii Hilo College of Natural and Health Sciences, and they were established in 2007. Here is this very pretty picture of Helilani rover, which is operated by PISCES. Of their projects and programs, the reason why I want you all at Space Resources to know about it is because they do a lot of volcanic basalt research for in situ resource utilization. And they leverage Hawaii's history and geographic uniqueness to do this kind of research. And so I want you all to know about them because I feel like they're under leveraged. Christian, Amber, and Chris do such a good job to facilitate the aerospace industry development in Hawaii. and they provide a lot of internships for robotics and material science. They've done such a good job with STEM education programs and community outreach. And if you're thinking about how you could leverage Hawaii, it is a prime location for LEO launches. Hawaii, as you know, is near the equator and advantageous for space launches and satellite operations. As you saw in this talk, it is an ideal lunar and Martian analog terrain. And we really treasure cultural sensitivity when it comes to doing our research. And so we think about Polynesian wayfinding, living off the land, and exploring new frontiers, and bring that into the kind of futuristic space exploration that we're doing today. All right, I'd like to acknowledge the wonderful people that I've worked with. These are just some of the amazing researchers and students that I've worked with on these projects. Thank you to NASA, NSF, and the state of Hawaii for funding. And with that, you can get in touch with me about either the space robotics research I was talking about, or if you're trying to develop your own aerospace curriculum, I've done some of that. So yeah, come say hi. Here's my email, and I will take any questions at this point.
Awesome. Thank you, Frankie. Really, really cool stuff. Near and dear to my own heart. Yeah, people, go ahead. There's nothing in the Q&A yet. Go ahead and pop stuff in there though. I have a million questions, but one that I'll ask just because I'm curious. You mentioned you did a really cool diagram of computational complexity versus
Yeah.
versus feasibility for integration into a robotic system, and you talked about how for something like a discrete element model, we can't just put that on a rover because, I mean, we can't just strap a workstation or supercomputer and send it off to space.
Right.
With that in mind, what kind of compute hardware are these things usually run on? What type of processors do you guys usually use? I'm actually not familiar with that part of this.
That is a great question. So we in my lab, and these are not spaceflight hardware. We use these NVIDIA Jetson
Yep.
computers.
Okay.
And so, yeah, and we specifically run it on these embedded computers. They are beefier than, say, like the BAE computers that are on the Mars rovers. But I think what's really promising is that Ingenuity proved that you can fly algorithms on like a Snapdragon chip, which is like on iPhones or other phones. And so it is a COTS component, and it did successfully crunch through a bunch of numbers and algorithms in space. So I can see us transitioning, say, an NVIDIA Jetson Nano onto like a smaller Cadre rover.
Super cool. Thank you.
Yeah.
Uh, Also, what do you see as the biggest challenge going forward in particularly algorithm development, not on the hardware side, on the software side for your
Oh my
field?
gosh. So I'm gonna rephrase the interpretation of the question. So on the software side, I think that yes, it is a very technically hard problem, but I think there's a soft side of this of technology adoption where I think I face a lot of resistance from NASA engineers or program managers because they're not sure about how interpretable these algorithms are. And so there's a level of safety that is required of these high risk missions. And I think proving interpretability or guarantees or safeties with these algorithms is the biggest obstacle.
No, well put. And yes, you interpreted what I meant correctly. Thank you.
Okay, cool.
I had a question or two while we're waiting for some to come in as well. So in that same diagram, Jared brought up earlier of a sort of error versus computational load. They're
Mhm.
conflicting objectives. Which did you find to be more difficult to minimize?
Oh, so I think that accuracy or error is more fundamental to the model. And so we've been very strategic in, I was talking, there's another dimension to that diagram. Sorry, I'm like going on a ramble, but the diagram, yes, is error versus computational intensity, but I think that we're choosing the physics-based model because there's this other dimension I didn't show that is interpretability. We've really liked the physics-based dynamics model because I think there is a clearer path for adoption. Okay, back to your original question about like what is harder, getting the error down or getting the computational intensity down. So I think that error is more fundamentally limited by the model that you choose, whereas computational intensity, there are some engineering tricks of like doing matrix inverses more in a leaner way. So I think it's easier to get computational intensity down, harder to get error down. Thanks for the
Well
question.
put.
Yeah.
Perfect. One did come in the chat, Joe, and I'll actually take that one instead of rambling on our own. So Parker Bradshaw asks, for the lunar environment, there are plans to put compute in orbit that would be accessible to lunar surface assets. Do you see this infrastructure as useful to real-time mobility algorithms and mapping?
That's a great question. I think that it's very interesting to distribute computation across multiple agents. I think the real question here would be, what are the timescales needed for certain algorithms? So I love that Parker was talking about real-time mobility versus mapping. I think that mapping has a much longer time constant that it's concerned with, and so that actually makes sense to measure something, generate a map on board something that is further away because there's this time longer delay. That's okay. But for real-time mobility, those time constants are like on the millisecond magnitude. And so if that communication delay is longer than milliseconds, then it doesn't make as much sense. Great question.
Thanks, Frankie. And yes, good question, Parker. I don't. Go ahead,
I
Joe.
can jump in with another.
Please.
Next steps, sort of improving the algorithms and your work.
The next steps would be to, I think, apply this to a real life mission. I think that we've done enough hardware demonstration on ground where we have come up with good dynamics models and good performance for the active learning algorithms that we've developed. We just want to see it in an actual spaceflight mission. So I've been collaborating with the cadre folks to see if we can get their data and to crunch it through the dynamics models that we're interested in fitting the data to, so that we can see that we can actually be predictive of a real life lunar rover. And I know that's going to be further into the future. But after that would be like adoption for real time. Seeing them demonstrated in missions in real time where we let go of the human interaction.
Nice. That's pretty exciting. And I think I know the answer, but just to confirm, you were talking about using it for identifying like highest deposits of water. I'm imagining that it's relatively agnostic to the sensor. Like if you wanted to look at aluminum or something, you just swapped out the sensor.
Yeah, thanks, Joe. Yes, that is great advertisement for the work that I do. It is agnostic to the kind of science objective or the payload measurement, just as long as the mapping itself is like a continuous manifold. Right now, we're working with strictly like position to some kind of scalar mapping, so 1D distribution. But in the future, we're going to look at mapping to multiple dimensions. So not only, let's say we'll use water ice, but we also want to map like material composition of aluminum. That would be two different mappings. And so we are working on incorporating active learning for multi-objective missions.
There's still nothing in the Q&A, and sorry to just hit you with all these questions, but
No, I love it.
I did just scratched the surface of swarm robotics in my early graduate career, and it was all terrestrial geologic mapping, ground temperature stuff around volcanic features. And one thing that our learning models were having troubles with was something like sharp discontinuities at, say, a fissure in the ground where you have steam or just general hot in mapping and following that sort of thing. And again, we just barely got into the algorithm development and robotics on this before we had to go off on other directions. But how do your models handle that sort of realistic geologic context? How do you work in that sort of thing into a smooth model?
That's a great question. We are also finding that really difficult, and that's something that so in active learning, the model that underpins the algorithm is called a Gaussian process, and it is a very generally smooth manifold that it tries to map upon. But there are other basis functions or expressions that build a model that can handle discontinuities. And so we've switched our active learning model to not use a Gaussian process with a certain, sorry, with this certain basis function. We've transitioned it to use something called a matern kernel, which handles these discontinuities more. But I think fundamental to your question is like, are the basis functions that build your model, can they represent discontinuities? I've also modeled discontinuities like collisions between spacecraft using exponential functions. I know that neural networks are better at modeling these discrete events if like there are neurons that are dedicated to representing a feature like that. So yeah, I think it's like specific to the model that you're working with, and we can take this offline. I'd love to talk about it.
Of course, yeah, sounds great.
Yeah.
Anyone
I,
else in the Q&A? Oh, go ahead, Joe.
I had one more,
Yeah.
while I'm still waiting. Are there any rover characteristics in particular that you would say are ideal for implementation? Or is it just the actual, you know, rover system that you implement and not really matter?
Yeah. I think logistically, it's better to start off simpler with these rovers. So, for example, the Cadre rover is a very simple shoebox. It's got 4 wheels that are originally attached with not much of a suspension system. It has differential drive. At least I think so. But the simpler, the better when it comes to creating these dynamics models, because I think it is a very complex, hard physics to model. And so the simpler the rover geometry is, the more knowledge we have of it, and the better we can just focus on the terrain wheel interaction instead of modeling the suspension system as well. Thanks, Jeff.
Cool. We have one in the chat from Hunter Williams. Could this active learning model be used for more generalized robotics purposes? E.g., could it be used for automation of both an ISRU payload and its mobility system together?
Yeah. Okay. So we can see active learning used in a lot of different applications. I think I might be interpreting this a little bit off, but we have seen it used in remote sensing applications as well, where the thing that you're trying to map is maybe some ISRU metric. And your orbiter, it has the ability to point its remote sensor at a certain location to do this mapping. So I could totally see it being used for an ISRU payload that's not necessarily on a rover. For mobility, we are also looking at active learning for learning dynamics. I hope I'm interpreting this question right. So my student, Hans, is looking at, okay, instead of mapping position to, say, water ice, why don't we map robot state to robot state, or like robot state in action to robot state. So the search space is the robot state in action instead of just position. I hope I answered your question in the way that you wanted it to be asked. Okay, cool.
Hunter says, thanks for working through my badly worded question, Frankie. Perfect.
No, great question, Hunter.
Parker Bradshaw asks, Is this learned mobility algorithm sufficient to robustly avoid rover entrapment, or would that be handled separately from trajectory following?
Great question. Okay, I feel like that's a huge problem. Rover entrapment, I think might be more of an obstacle from the perception point of view. I think it's really hard to anticipate when there are sand traps right in front of you because they visually look the same as just the surface that it has solid ground beneath it. Until it's too late, until you're like in situ trapped there. So visually, I don't think there are that many cues. If there is some kind of haptic clue, maybe we would be able to detect entrapment before it happens, but I'm not really familiar with techniques about that right now. I think that's a good question.
Agreed. Cool. We'll give it another minute for people to enter things in the Q&A. Uh, I'm just about out of questions I can think of off the top of my head. Um,
Yes, sorry, I went a little fast. I did have more
no.
material about satellites, but I felt like it wasn't relevant to space resources.
Oh, it absolutely is. It all ties together, every last bit of it. But I get your point. Well, here we go. Oh, whoops. Sorry. Hold on. I accidentally added someone to
That's okay. I can read the question that William
there we go.
posted
Sorry, here we go.
regarding.
Regarding the terramechanics modeling system ID, how are you factoring in effects of lunar gravity at your analog test sites compared to in situ?
That's such a good question. Yeah, so gravity is definitely different, and we are not really factoring in effects of gravity in the hardware or experiment configuration per se. We are just we're like taking gravity at 9.81 and putting it into the model. And then assuming that if you were to plug in like a 1.66, that the dynamics would representatively scale for a lunar environment. But there are people at mines, for example, Ian is building a planetary surface analog testbed that has a gravity offloading mechanism using like a crane and tethers. So that is definitely something we are going to look into the future.
And I will make a shameless plug. UCF has something similar that's coming
Oh,
online
yes,
soon.
absolutely. Yes.
And no, we will be collaborating with Colorado Mines on this as much as possible, of course. Um
UCF is the OG.
oh no, it's right along the same timeline actually. Uh
Mm.
anyway, one more came into the Q&A. William Foster Hall asks regarding the Terra Mechanic. Oh, I already answered that one. Sorry, I just didn't dismiss it. Okay. But yes, one point I do want to make that I will just throw into the intellectual soup. This is a bit out of my role as host, but the gravity offloading of rovers is interesting because it doesn't offload the gravity of your simulant, and
Yeah.
hence you're simulating a less strong interaction with the regolith. For example, a gravity offloaded rover is going to have a harder time shearing the regolith since that regolith is in at its full strength in normal gravity, Earth gravity. So in testing, I think it's actually probably better to not gravity offload in a lot of cases if you're interested in testing for worst case scenario. Just some thoughts I've been having, everybody.
Great point, Jared.
There's
But
a
no, go ahead, Joe.
there's a really interesting paper that recently came out that scale wheel diameter to account for that.
Okay.
I don't remember
Well,
the name of it, but if you try and find it, it's actually really interesting.
cool.
That's a key problem.
Yeah, no, absolutely. All right. Well, now that I've distracted everybody from the main point of this webinar, sorry, Frankie. I
No, great
don't
point.
I don't see anything else in the Q&A. Um, so I and Frankie had her email up on that one slide. So if you guys have any questions, please reach out to Frankie or myself or Joe. But for now, I think we can call it, depending on your time zone, a late afternoon. Frankie, for you in Hawaii, a late morning. So everybody, thank you for attending yet another one of our webinars. Frankie, thank you for an awesome and informative talk. Really cool stuff. And we will plan to see you all next month.
Thank you so
Thank you.
much.
Awesome. Have a good one, folks. Bye.
Bye.